Okay, so our next topic we'll talk about martingales, and in this lecture I'll cover really just the basic definitions and some of the technical background that we need to fully apply martingales and use its theory to study really general class of stochastic processes. And there's quite a bit that can be done, and it's quite an important area in the study of stochastic processes. We've already encountered several martingales already, and we will. I'll bring those up as examples of martingales as we go on. So a martingale, really going back into the history of probability, is a model for a fair game. So it's the idea of a process in which the expectation of where we are after the next step is the same as where we are right now. So if you think about playing a fair game, tossing a coin with a 50-50 chance of heads, and we win $1 when it comes up heads and we lose $1 when it comes up tails, then the expectation of any given toss is 0, and we can accumulate our wealth over a large number of trials. And so after some number of trials, n, or 100 trials, we may have won, we may be at +5 or +10, we may have won $10. But the expected, and then we can ask, well, where do we expect to be after the next toss? Well, where we expect to be is going to be wherever we are now, plus the random variable that is determined by this toss of the fair coin, which has expectation 0. So we don't expect to go up or down in that one in the next step. And so that's a simple and classical example of a martingale. There are many others. Okay, so the idea of a martingale, as I just alluded, refers to and requires the use of conditional expectation. And so what I'm going to do now is I'm going to review some basic measure theory, which is not assumed. So everything we've been doing so far in this class has been in the absence of measure theory for the most part, and the idea of a martingale can also be communicated effectively without going too deep into measure theory, at least the intuition for it. But we do need some basic measure theory to make these ideas somewhat precise. If you want a fuller treatment, you should take a higher level course in measure theoretic probability. Okay, so we're going to let omega fp be a probability space so just to remember what this means, omega is a sample space. This is the set of all possible outcomes. F is a sigma algebra or sigma field over or on omega, and P is a probability measure on the measurable space omega F. So just to remind you of what this means is a definition. A sigma field, so a sigma field on omega, and I'll usually just write a sigma field, but it is defined as a sigma field with respect to a particular sample space. So the sample space comes first, then the sigma field, and then the probability measure. A sigma field is a collection of subsets of omega, and we'll denote it by script F, such that omega is an element of the sigma field. If A is in the field, then its complement is in the field. And if we have a countable collection of elements in the field, in the sigma field, then their union, the countable union, is also in there. And the interpretation of these axioms, which you've probably heard, if you've ever seen this material before, you've heard this. You've probably seen an explanation like this. This is a mathematical axiomatization of the idea of some of the class of all things about which we have information. So if I'm interested in talking about in stochastic processes, we're interested in classifying whether or not a particular event falls within whether a particular event happened or whether a particular outcome satisfies a particular event. And so in this case, if we are checking, so these are all of the sets that we can think about checking whether or not they happened. So in particular, if we're interested in the set of all possibilities, then if we observe something, then we can certainly check, is this one of the elements of all the set of all possibilities? If we know that A did happen, or if we can check whether or not A did happen, we can also check whether it didn't happen, right? Those are, in some sense, logically complementary or equivalent events. And if we can check that each one of a class of elements of events happen, then we can check whether one of them, at least one of them, has happened. Okay. Now, when we talk about martingales, we're talking a martingale is defined a stochastic process. It's a property of a stochastic process. So the idea of a sigma field is one that works when we're talking about a single random variable. A martingale is one that is a property of a class of random variables, a stochastic process. And so for this, we have to define the idea of a filtration. And what a filtration is it's a family of sigma fields and it's a family that's indexed by some set, which I'll write as capital T. And capital T, in our case, is going to either usually be the positive integers. So positive integers including 0 or the positive real numbers. But in general, really, I guess this technically can be defined for any partially ordered set. But what we're thinking about T is we're thinking about indexing this set of sigma fields by time. So it's a family of sigma fields such that each ft is a sigma field on the space omega, and if for all pairs of times s less than or equal to t, fs is a sub-sigma field of ft, meaning that fs is a smaller sigma field. It contains less information. So the intuition here is that the idea of a filtration is that as time goes on, we're better able to filter the information that we've observed. The information we have at an earlier time, s, is less than the information that we have at a later time, t. Okay. And so a very simple, so an example of this would be if we consider rolling a die at each time, Then the amount of information we have after the first toss is, well, we can always have, these elements are always in any sigma field, but we also know whether or not any of the outcomes occurs, or we have unions and intersections of these measurable combinations, where here I'm writing AI to be the event that I occurred. And in general, F2, so F2 is going to be the information we have after 2 tosses of the die, so we will know whether we can know whether or not what the first outcome was and what the second outcome was for all possible choices I1 and I2, and also combinations, and so on and so forth. So Fn is going to be set of all measurable combinations of the first n tosses. So the information that we have after n tosses certainly contains the information we have after 1 or 2 tosses, because what we can do is we can combine these events. We can combine the events that we can combine several of these events together to tell us that, for example, if to tell that the first roll was a 1, we can of course take the first 2 rolls being a 1 1, 1 2, 1 3, and so on. Okay. All right. Okay, so that's a basic definition of a filtration. So where a filtration comes in is when we start to define a filtration, and we consider that we want to think about this. We have an increasing sequence of sigma algebras, so we have an increasing collection of information. We also have we have a process that's evolving in time, and how that process relates to its filtration is one that is related to the idea of measurability of random variables. So just a definition here is that if we have a sigma field, F is a sigma field, and X is a random variable. So as we've been talking about, we're talking specifically about real valued random variables here, although especially in the case of Martingales. So it's a real valued random variable, so it's a function. So remember what a random variable is it's a measurable function from a probability space to the real numbers, and the real number is equipped with the Borel sigma field, which is essentially just the collection of all intervals and combinations of intervals. You can take unions, intersections, and various limits of intervals. Then we say that, well, by definition, so it's embedded in the definition of a random variable that it's a measurable function. But what that means is, so we say that X is F measurable, and the notation that I'm going to use is either X like this, meaning that X is measurable with respect to F, or simply I'll sometimes write that X is in F, which again, the meaning of which should be clear when we write the condition, which is that X is F measurable if the inverse images, so in particular if the inverse images of all of these intervals, which is the set of omega such that x omega is less than or equal to x, this set is actually in the sigma algebra F for all values of x. So if you if you want to know why this is, well, this condition turns out to be sufficient to check that a random variable is measurable with respect to the Borel sigma algebra on the real numbers. Why is this an important condition when we talk about, well, in terms of probability, is because one of the things when we study random variables, we talk about the distribution. The distribution is determined by its distribution function, and the distribution function is determined by events of this form, whether or not the random variable takes values less than or equal to a particular value. So this is why that is important. Okay. And so for any random variable, we're going to define kind of a canonical or a natural sigma field. We define sigma of x as the smallest. So we're interested in the smallest sigma field with respect to which x is measurable. Okay, so this is sometimes called the sigma field generated by x. So one way to think about this is the sigma field that contains all of the information that can be measured directly from x. It's effectively all of the measurable functions of x are all kind of nice or reasonable functions of x that we might be interested in asking. Okay, and so where this gets us is that we can define a process, and we're close to defining a Martingale, but there's a lot of kind of preliminary work, which is that we define a process. So if we let x be a stochastic process and f be a filtration, then we say that x xt, and I'm omitting the so it becomes a bit cumbersome to always write this notation where we index over all time points, but since we know we're talking about processes, I'm going to be a little bit abusive of the notation to say that xt, the entire process, is ft adapted. So the process is adapted to the filtration if xt is measurable with respect to ft for all t. So this is a process version. You can think of this as a process version of measurability, where we have a filtration, a collection of sigma algebras, such that the process is measurable with respect to the corresponding sigma algebra at all times. And we write ft superscript x for the natural filtration, which is defined by ftx equal to sigma of the process up to time t for each t. So this is now what we will, this is the key idea in the study of martingales, because if we go back to the example of the coin tossing and plus and minus 1, we have a sequence where we're accumulating information as the process evolves, and one thing that we're particularly accumulating information about is, of course, course, how much money we have, but how much money we have in addition to the path of how much money we've had at all previous times. And so what we're interested in now is, we have a process, which is the money we have, and that process is measurable with respect to the past events of the game that we played. And so that's the filtration that we would be talking about in that case. Okay. So now in order to formally define what a martingale is, we have to define the idea of conditional expectation, which is actually a pretty subtle concept that you really can't fully appreciate until you study, or you can't really appreciate what it means until you study it in the higher setting, in really the rigorous setting of measure theory. But we can get some flavor of what it is. I think there is some intuition for what conditional expectation means, and here I'm just going to give the definition. So the definition is that if we have a random variable which is integrable, so finite expectation, and F is a sigma field. Okay. Then the conditional expectation of X with respect to the sigma field is a random variable which satisfies two conditions. First of all is that Z is measurable with respect to the sigma field F, and how it relates to X is that for all measurable sets in F, the conditional expectation of X restricted to the set A, actually, it's not conditional expectation. The expectation of X restricted on the set A, so we just take the indicator, is the same as the expectation of Z restricted to the set A. Okay. And so the idea here is that Z is a smoothing of F, of X over the events in F. Okay. So when we talk about, conditional expectation, importantly, conditional expectation is a much more complex concept than ordinary expectation, because ordinary expectation is just a single numerical value, the mean of the distribution. But the conditional expectation is itself a random variable, because what it does is the conditional expectation given the information that's in a sigma field, right? So it is actually a function of the random variable. It's a function of the outcome of a random variable X, where we might only get to observe partial information about the value of the random variable X. Okay, so an example of this would be if we're talking about tossing a coin 10 times, I can tell you what happened on the first 5 of those tosses, and you can condition on that information to give me a conditional expectation of what's going to happen in all 10 tosses. But that information on the first 5 doesn't tell you deterministically what's going to happen on all 10 tosses. It only allows you to kind of whittle down the distribution and smooth over, so you're smoothing over all of the events that are measurable with respect to those first 5 tosses. And on those events, the answer will be the same as you would have gotten by just taking the expectation of the original random variable. Okay. Now it turns out that this is, as stated, just a generic statement about a property of a random variable z, but in fact this is a unique thing. So there is a uniqueness statement here, which is that, let me just state it. Which is that if we have two candidates for conditional expectation of x with respect to sigma field f, then they must be equal almost everywhere. Okay, in particular the probability that they are equal is 1. Okay, and there's a way to prove that can be proven. I won't prove it here. We're going through several. There are several technical properties of conditional expectations that we need to record before we can use, because they come up and they're useful in our study of martingales. And I'm just going to list them here, and then we're going to move on. So the first of these, and a lot of these properties are familiar properties of ordinary expectation, but in fact these are different properties because they're properties, again, of a random variable, not a property of integrals, which is what a Lebesgue integral, which is what the ordinary expectation operator is. Okay, so linearity is just to say that the conditional expectation of a linear combination of random variables is the linear combination of the conditional expectations. Okay, we can also conditionalize on, and the real value, or the real trick that we get to use, that makes conditional expectation so useful, is that if we have a random variable z that's measurable with respect to the sigma field that we're conditioning on, then we can take it out of the expectation operator. So the conditional expectation of, say, zx given f is equal to z times the conditional expectation of x given f. Okay, and again, this is equality as a random variable or as a function. Okay, so this is still a random variable, but this was also a random variable. Okay. Another property that we've used before in some way, the Tower property of conditional expectation, which is in a sense related to the law of total probability that we've made use of, but it's a bit more of an involved definition, which is that if we have a sub-sigma algebra f prime of f, then we can iterate the expectation so that the conditional expectation of x with respect to the larger sigma algebra, and conditioning that on the smaller one, is equal to just the conditional expectation of x with respect to the smaller. And one more for now is conditioning on independent is in the case where the random variable is independent of the sigma field. So if x is independent of f, then the expectation of x with respect to f, conditional expectation, is just the ordinary expectation of x. Okay. Now there's some notation that I've put here, and I try to stick with this notation, although I can't guarantee that I will 100%. Is that I use the boldface E for the expectation operator when it's an ordinary expectation operator. So this is an integral operation, whereas this is not an integral operation. This is a random variable. I don't use the boldface for that. That's not necessarily used by everybody, but it is sometimes good to keep in mind that these are fundamentally different objects, even though we do use similar terminology to refer to them. Okay, so now we're ready to define what a martingale is, and what we have is, so the definition that we have for a martingale is that a process ZT is an FT martingale, which I'll sometimes write just as MG. And what I mean by FT martingale, again, this is over all times, and FT is a filtration. But what this means is that it's called an FT martingale if ZT is FT adapted, so the process is adapted to the filtration FT. Each random variable is integrable for all t, and the key definition is that for all s less than or equal to t, the conditional expectation of the process with respect of xt with respect to fs should be zt is zs. Okay, and this is for all t. So that's the definition. Okay. And let's see some examples or make some observations about this, and then we can conclude this lecture. But this is the definition of a martingale, and this is the key condition here, which is saying that wherever we are, if we condition on what we know and where we're at up to time s, then we don't expect to be any better or any worse off. We expect to be in exactly the same place we are now at any point in the future. Okay, and that's why this was originally presented as a model for a fair game, because in a fair game we should not be expecting to win or lose on any time scale, at any time in the future. Of course, there will be fluctuations, but in terms of what we expect, we can't look forward and actually expect to be in a better or worse position than where we're at, or else the game must not be fair. Okay, so some initial observations. Okay, first of all is, I'm just going to write this down. If we let Fn be the sigma field, so I'm going to actually take a discrete time process here, let it be the process that is generated by all states of x up to time, or z up to time, n. Okay, So this is the sigma field generated. This is the natural filtration for this process. And you think about it as the filtration contains, kind of all of the information, but no extra information about what the process has done up to time n. Then on the one hand, if Zn is a martingale, with respect to this filtration, then on the one hand, by definition, the conditional expectation satisfies this as usual. But really, it's enough to just condition on the first. It's the same as conditioning on exactly the states of the process up to time n, because that's what the sigma field actually just contains that information. So if you think about conditioning on all of the information in collections of, say, 100 of the first 100 coin tosses, it's the same as just conditioning on our wealth pattern up to the first 100 tosses, because our wealth pattern of winning one, losing one, contains all of the information we need and all the information we have about those first 100 tosses. Okay, but by this observation, or using this observation for any non-negative value k, we can take the conditional expectation of z at a time in the future, k units into the future, and we condition on fn. Here we use the tower property by conditioning on first a larger sigma field, so fn plus k minus 1 is larger than fn. So we're using the tower property. This is true by the tower property. But here what we use is the fact that, so we're using the fact that fn is smaller. But this is just equal to zn plus k minus 1 by the Martingale property. And so now what we have is we've reduced the index by 1, and we can iterate this for all values k bigger than or equal to 1, and what we're going to end up with in the end is the expectation of Zn given Fn, and Zn is Fn measurable, so this is Zn. So starting with just this condition, we can actually derive what appears to be a more general condition here, where it holds for all values into the future. At least in the discrete time case, that's easy to do. Okay. All right, so to conclude this lecture, I'm going to do it by just going through a number of examples. And the first example is the one that I started with, which is the simple random walk, which is essentially a simple random walk martingale, but it doesn't have to be a simple random walk. So if we construct a process from an IID sequence of random variables, each having mean 0, so we have a mean 0 sequence of random variables, and we define Zn to be the nth partial sums. So this is just a very straightforward process. And what I'm defining is, what I'm also doing is I'm assuming in all of these examples that f is the natural filtration. So I'll write it down here, but if I don't specify what the filtration is, you should assume it's just the natural filtration, or in this case it's actually the filtration that's generated by the x random variables. Okay? Okay, first is to show that this is a martingale, we have to show that it's adapted to this filtration. So Zn is Fn adapted. And I'm not always going to show this in the examples that I put here. You should verify this as an exercise, but you should verify this as an exercise. But bear in mind that it does need to be done in general. Okay, so Zn is Fn adapted. So how do we know this? Well, what does it mean to be Fn adapted? It means for each n. So what this means is that Zn is measurable with respect to Fn for all n. Okay, so all n bigger than 0, but z0 is just a constant, so that's fine. What is Zn? Zn is the sum of the first n of these IID sequences, of this IID sequence of x's. Okay. Each one of these, so x1 is measurable with respect to f1 by definition, by construction. x2 is measurable with respect to f2, and so on and so forth. Fn is measurable with respect to Fn, but by definition, F1 is smaller than Fn because Fn is also and contains the information of x1. Same thing for F2, same thing for Fn, of course. So what we have is we have Zn as a function of terms, each of which is measurable with respect to Fn, and therefore it itself is measurable. So this is using some properties of measurable functions that we haven't rigorously developed in this class, but the idea is if I know the information, so intuitively what it means is that if I have the information that Fn gives me, I can compute x1. And I can also compute x2, and I can also compute xn. And since I can compute each of these terms individually, given the information in Fn, I can compute Zn because I know how to add things together. Okay, so there's certain types of functions that are straightforward and simple enough that allow me to combine properties of measurable functions. Okay, so it's adapted, and then to see that it's a martingale, we just verify the martingale condition for one step into the future, so based on what we just showed. And Zn plus 1, this is the sum of the first n plus 1 terms, but it's Zn plus xn plus 1. And we've already shown linearity of the operator, of the conditional expectation operator. So this is by linearity. Zn is measurable to Fn, so we're conditioning on effectively what's a constant, Zn measurable, so this is Zn. Xn plus 1 is independent of Fn because Xn plus 1 is independent of all of the variables that Fn is constructed from. So this is just the expectation of Xn plus 1, which we've assumed to be 0. So this is Zn. Okay. So that was an additive martingale. Example number 2 is a multiplicative martingale. If we instead of letting the x's have mean 0 and adding them together, we can also let x's have mean 1. So they're going to have mean 1, and we're going to multiply them together. So Zn is going to be the sum, or the product, of first n of these. Okay. And now what we have is we verify the condition, Zn plus 1 given Fn. Again, Fn is going to be the same sigma field as we've defined up here. Zn plus 1 is the product of these first n plus 1 x's, which we can express as Zn times xn plus 1. But now we have a similar situation we've seen before. Zn is measurable with respect to Fn. So we can take it out of the conditional expectation. But now xn plus 1 is independent of Fn, and so this is just the mean of xn plus 1. That mean is 1, and so this is Zn. Okay. All right. There's one more that I want to show, so these are relatively straightforward so far. The last one that I want to show here, which draws a connection to one of the previous topics that we've discussed, which is the offspring in a Galton-Watson process. So if we let Yn be a Galton-Watson process, so remember what that means. The Galton-Watson process is the number of offspring. We count the number of offspring alive at each discrete generation. So in each generation there are, before each generation, we're assuming there are, say, y sub n individuals in the nth generation, and each one gives birth to some independent random number of offspring for so for xn plus 1, xn plus 1, to IID from the offspring distribution with mean mu. Okay, mean of the offspring distribution. Okay, and what we're going to do here is we're going to define a new process, which is Z. Zn is going to be the number of offspring divided by mu to the power n. So remember, we actually did show that this converges to a random variable, that this converges to something in the, or we didn't actually show this. I recorded the theorem which said that this converges to a random variable, this Zn, when we scale it by mu to the power n. And what I said when we proved it was that the proof uses the Martingale convergence theorem. And so what we'll talk about later in a future lecture is the Martingale convergence theorem. But what we are defining now is showing that this is actually a martingale. And it turns out that once you show that something's martingale, you do get certain, in some sense, you get convergence results for free. So that's the consequence, and that's one of the nice applications of martingales. Okay. So first of all, we observe just in general for the Galton-Watson process, if we want to know what the conditional, so now we have to define, so remember Fn is going to be the sigma field generated by the Galton-Watson process, so it's the filtration. You can show that this is adapted, that Zn is adapted to this filtration pretty clearly, actually, because it's actually just a scalar multiple of Yn. Okay. But looking at each of these terms individually, yn plus 1 is the sum of some random number of terms yn of xn plus 1j given fn. And yn is measurable with respect to fn, and so we can treat it like a constant and pull the expectation inside this sum with a random number of terms. But now what we're doing is we're adding up a bunch of conditional expectations of quantities that are of random variables xn, which are independent of the Fn sigma algebra, and they just have the mean. The mean is the offspring distribution. That's just the mean, which is mu. So this expectation is mu times yn. And so when we express it this way, what we can then immediately observe is that the conditional expectation of zn plus 1 given fn, well, zn plus 1 by definition is the expectation of yn plus 1 divided by mu-n plus 1 given fn. Mu-n plus 1 is just a constant, and we've already derived what the expectation of yn plus 1 given fn is. So this is 1 over mu-n plus 1 times the conditional expectation of yn plus 1 given fn. We just calculated this to be mu times yn, so one of those mu's cancels. We get yn over mu to the n, which is zn. So we've shown that this is a Martingale. Okay, and we'll keep this in mind for later when we show that when we show the Martingale convergence theorem. Okay, and that's what we're able to use to prove the convergence in the case of the Galton-Watson process. Okay, one more example, which is called the Doob Martingale. Okay, so the Doob Martingale is, so it's named after Doob, but if we just take any random variable, so we let x be any random variable, and f be a sigma algebra, be a filtration. Sorry. Okay, so we need a filtration. So we take any filtration, and we define a process from this by taking the random variable x and just conditioning on a different piece of the filtration at each time. So then we define zt to be the conditional expectation of x given ft for each t. And we know by the definition of conditional expectation, I realize I just wrote this wrong. We know by definition of conditional expectation that this is automatically measurable with respect to ft. So zt will be ft adapted. And in particular, so automatically, so zt is ft adapted. And for any s less than or equal to t, what we can show is that the expectation of conditional expectation of the process zt given f of s, zt is by definition the conditional expectation of x given ft, right? But now what we have is, note that f of s, fs is a subsigma field of Ft, so this is just the tower property, that this is equal to expectation of x given Fs, which is Zs. Okay, so those were some, that was a quick and relatively quick introduction to martingales, and with some examples of things that we've seen, maybe some things that we haven't seen. And we're going to continue in future lectures to talk about how we can use this concept of a martingale to prove various properties of stochastic processes.